Well, welcome to the Radio Astronomy Special Interest Group for TAAA. The board approved us as a special interest group at their meeting last Wednesday. Gary and I gave a presentation and it took about 15 minutes. And I think it was a unanimous decision that we be authorized as a special interest group. Our plan is to meet the third Wednesday of each month at this time, 7 to 8. I'll be the coordinator for the group. Gary is going to be the alternate. And what we're going to shoot for in each meeting is to give a presentation. Part of it will be a presentation and part of it will be question and answers about projects that we're working on. At least that's the way that we anticipate it at the moment. Gary is going to be giving the presentation tonight about Scope in a Box, I think is what it's called.
Sure.
And each of these sessions, by the way, will be recorded. And then that recording, we will place it out on YouTube. It'll be unlisted on YouTube so that you'll need the exact URL to get to it to watch the recording, but they're going to be placed out there for you to look at. And we'll be sending out the URL to that recording to each of the people in our group. Okay, Gary, do you
Yes.
want to take it from here and
All right.
Your project?
So I got a bunch of slides that I'm going to show. The first, show my screen.
Oh, wow, that's beautiful.
All right. You should be able to see all that. Setup and use of amateur radio telescope for detecting H1. You can hear me okay and see that, right?
Yes. Yeah.
All right. Let me just do an adjustment here because. Okay. So here's the agenda for tonight for my talk here. Before we jump into the telescope itself, I thought it'd be helpful to talk about what is neutral hydrogen, what is this 21 centimeter line, what's causing that. A brief introduction to telescopes, parabolic dish telescopes. That'll be interesting. I think there's a lot of potential good information there that I think you guys might find to be very helpful. We'll get into my radio telescope setup, and then I'll do a demo. The Milky Way is kind of low right now, but I have some objects in there right now, so you can see what that looks like. So after doing the demo, I'm going to capture some data from the image that we have, and I'm going to pop it into a spreadsheet. We can look to see how that looks, calculate the radial velocities and stuff like that. And at the very end, I'm going to go through a overview of the software installation, some tips. We'll see how it goes. I have 32 slides plus the demo, so it might, the last part we might be kind of quick to get through the software, but the good thing is I'm going to be sending all this information out in a form of a zip file, the slides, the spreadsheet, all that stuff, so you guys can have access to it and play with it and see what you think. So I would like to ask just everyone just to mute your microphone. Sometimes little noises will kind of disturb things. And let's see, during the talk, you can ask questions, maybe put them into the I don't know if I'll see the chat or not, but you can ask questions, but most of the time we'll have at the end for Q&A. And also during the demo, there's when I move to a different object, it takes about 6 or 7 minutes for the image to form, and we can talk about stuff then too.
Gary, I'll monitor chat for you.
Okay, thanks. And as Sandy said, the recording will be in the TAAA YouTube location, and et cetera, et cetera. Okay, let's talk about the 21 centimeter emission from hydrogen. So neutral hydrogen, You're probably familiar with H2 regions. That's the ionized gas that glows a beautiful red color from the hydrogen alpha line. Neutral hydrogen is referred to as H1. Normally, it's very difficult to see. It's impossible. It does not radiate anything in the optical. It certainly could absorb light. So you have hydrogen clouds that could be absorbing light from stars behind. But in it itself does not emit anything in the visible or shorter wavelengths. Now, in 1944, during World War II, there was a Dutch astronomer, Henk van de Hulst, and he calculated that H1 neutral hydrogen should be able to issue a radio signal, but the war was in the way, so they had to wait until the end of that. At the end, there was a lot of this surplus radar equipment, so a lot of organizations started grabbing these and starting to hunt for these elusive H1 signals, and they actually saw it for the first time in 1951. So that's been out there for quite some time. But the big question is, what exactly is going on in the atom? What's causing this signal? So this little complicated diagram, basically, there's a thing called electron spin. Both protons and electrons have a thing called spin. The protons and the neutrons are not spinning, but they have a behavior that it's as if they have angular momentum, as if they were spinning. And because they are charged particles, as a result of that, the proton and the neutron in the hydrogen atom act like a little tiny bar magnet. And in that diagram, you can see, I don't know if you can see my mouse, but here's the proton. And the left side here, by the way, this represents the ground state for hydrogen. And in that state, the proton has its north pole, if you will, pointing up, south down, and the electron is the exact opposite. Now, through the course of things, collisions with other hydrogen atoms, perhaps another 21 centimeter line might hit it, the electron will actually do what they call it a spin flip. That's the right side picture here. And in this case, both the poles are pointing in the same direction for the proton and the electron. And as a result, there's a little bit of a magnetic tension, if you will, that's pushing against them. And that actually is a higher energy state. Not a very big one, but that's exactly what that is. Going to the next slide, here's another simple diagram. Normally, when you're in this excited state where they're both spin is in the same direction to both the poles, when the electron spin flips, it gets to a lower energy state, and that's when this 21 centimeter wavelength photon shoots out. And that's what we're looking for. Now, interestingly, the mean life of these neutral hydrogen atoms in this little exaggerated energy state takes about 10 million years to flip, which I just thought that was absolutely bizarre, like 10 million years. How did they even figure that one out? And by the way, I'm not a scientist. I don't play one on TV. So I don't understand the quantum mechanics behind that, but they've been able to figure that out. The H1 clouds, they actually are a more perfect vacuum than we can create on Earth. But even so, or because of that, I should say, it usually takes, or roughly takes on average about 400 years for two H1 atoms to actually collide. So we've got a couple possible outcomes. So if one atom is in the higher energy state, if it gets hit by another hydrogen atom, that could trigger a spin flip to the lower state, but it actually does not emit the photon. I think it's partly absorbed by the collision itself. However, if it's in the ground state, it could possibly flip and go to the higher energy state. One of the things I was wondering about is, if this got a 10 million year mean life, how come we can actually see it now? Because the universe is what, 13.8 billion years old? Well, it's because of this collision can actually put them back up into that higher energy state. So they get popped up, they stay there for 10 million years, and they come back down. So H1 atoms are mostly in the plane of the Milky Way, and there's lots of them, and that's why we can actually observe them. Even though it's almost a perfect vacuum, there's so much out there. So let's talk about, that's the H1. Any questions on that? Talk a little bit about parabolic radio telescope properties. So we're all familiar with this picture of a kind of prototypical radio telescope parabolic dish. There's different configurations you can have. This one's a Cassegrain design, and essentially you've got the main mirror, of course, or the main dish, reflects the radio signals just like optical our telescopes reflect the optical waves. It's a subreflector and shoots back down to what they call a feed horn. So all radio telescopes have feed horns. That's the place that actually measures and detects the radio signal. In our simple example that we're working on, our little Wi-Fi or scope in a box, it's not a Cassegrain, so we actually have the feed horns right at the top here. And of course, once the signal is detected, there's a little antenna inside of the feed horn. Then information is passed into a receiver amplifier, and then we can actually see something on our computer screens. Now, radio telescopes, they're not like optical telescopes. With an optical telescope, you can have your CCD or CMOS camera sitting on it. You create this beautiful two-dimensional image of galaxies, nebulas, etc. But essentially, you can't do that with a radio telescope, at least not directly. Radio telescopes create the equivalent of one single pixel. It's a big one. The smaller the telescope, the bigger this field of view of the pixel is. But that's really what they are. If you want to create an image, for example, you want to look at, maybe you're looking at a part of the Milky Way and you want to try to graph and see what the arms look like, or the regions of thicker or thinner density. You can do that, but what you have to do is essentially you have to imitate what you do with a CMOS camera. You take an image, you move the telescope, take an image, move the telescope. You do this repeatedly like a grid pattern, and eventually you'll have enough data that you can synthesize an image of some kind. Now, there are some professional telescopes. They actually have a focal plane array of receivers that mimic having multiple pixels, but they're very small. They don't have a whole lot, so they actually have to do that same kind of grid pattern. There's also a thing called aperture synthesis, where you've got telescopes using interferometry across the globe, using the Earth as the baseline. That it's very complicated math that they do, but that's what they use to generate that beautiful picture of the black hole in Sagittarius. All right, now here's my itty bitty scope that I did in 2012. This is an example where I wrote some program to go in and take an image of the sun and then move the telescope a tiny bit, 0.3 of a degree, take another image, 0.3 of a degree, and I went through this grid pattern. And what you can see here, I created a three-dimensional picture of the intensity, and you've got right ascension and declination here. You can kind of see how you can actually create something. And then, of course, a two-dimensional view looks like this, with ever-increasing intensity as you get to the center. So that's how you can do your imaging. And with our 21 centimeter hydrogen lines, this particular little scope has, this is a typical low noise block that you would get for any satellite receiver. And the wavelength is much shorter than the 21 centimeter. So the field of view of this is about 4 or 5 degrees. As you'll see in a few minutes, we talk about the actual side of the field of view of our neutral hydrogen telescopes is much bigger because the wavelengths are much longer. Right. Let's talk about something about, they call it a beam pattern. Now, I don't claim to be an expert on this stuff, on antennas. I'm not a ham operator, so you ham operators probably know a heck of a lot more about antennas than I do. But this is a very typical image that I've seen in different publications, where they represent it's a way of looking at the telescope, what it can see, but they act as if it's actually emitting like a signal, like a radar signal. So you've got this interesting, it's a three-dimensional, like lobes they call it. So you have the major lobe. So if the telescope is pointing in the Z direction, that's where you get the most signal in that direction. Now, based on the size of the dish itself, the larger the dish, of course, you'll have better resolution. But they have a way of measuring that, just similar to what we do with our optical. They call it half power beam width. That's the exact analogy to our full width half maximum that we do in our imaging. So that's this right in through here. You can see my mouse going back and forth. Now these little side lobes down here, it's an interesting, I was wondering what those were initially, but it turns out, just like we have an airy disk, we use optical telescopes and you have those concentric rings around the center, the lobes are essentially your concentric rings, but they're a radio version of that. And the side lobes are bad. People do things to try to reduce the telescope actually picking them up. And that's part of the design of the antenna or the dish itself, is to try to minimize that. And also where you place the feed horn would make a difference too. Here's another way of looking at that, just like a cross section through there. And if you can imagine looking at an airy disk of a star in a telescope, optical telescope, if we do something like this, of course, this distance would be much smaller, but you would have these concentric rings going around just like that. So it's the same idea. And just like we don't like them too much, we don't like to have central obstructions in our optical telescopes. Same applies to radio telescopes. If you can get rid of the central obstruction, these side lobes are reduced as well. Any questions so far?
Yeah, Gary, we've got a question from Doug. It says, on this DirecTV dish, looks like the normal feed horn.
Yeah.
Did you have to modify the feed horn at all?
No, what I did was, that's the itty bitty telescope design. Basically what you get is you use a satellite finder. So when someone comes and installs a satellite dish at your house, they put the dish on the roof and they use this little satellite finder to essentially aim the dish at the satellite that they want to aim it at. It's got a little analog gauge on it. And so that's exactly what I use, although I did some other things to it to actually extract out the signal and get it into my computer. But that's exactly it. It's just it's the standard, they call it low noise block, the feed horn. I bought that off of eBay. It worked great. Hope that answers your question. Okay, resolution. Works the same way as an optical telescope. You just measure the diameter of the dish. That's the key factor. And the calculation for that is, if you get it in radians, it's 1.22. This should look familiar because this is the same equation that we use for optical, except now our lambda, which is our wavelength, is much, much, much longer. So for H1, the lambda is 21.1 centimeters. And so for our example, our telescope, our 1 meter, it's 100 centimeter. We get a field of view of 14.7 degrees. Now that's essentially one big honking pixel. I know Bill up in Flagstaff, you got a 3 meter dish. So your resolution's a lot better, 4.9. That's still pretty big. So the conclusion you can come to, just like optical, size matters. The bigger the dish, the better resolution. Although there is a physical limitation in terms of how big these dishes can get. And the way they circumvent that is to get into interferometry, which we won't be discussing tonight, but that's how you can get better resolutions. So 14.7 is about what we're going to get with our Wi-Fi, 1 meter Wi-Fi grid antenna. Now, there's a whole bunch of other things you can talk about, which we're not going to do tonight. You get into antenna theory, dish configurations, prime focus, cast grain, offset, different designs for feed horns and amplifiers and filters. One of the big factors is reducing noise coming from the electronics. There's an extra E in there. Just from heat, can cause problems with local radio frequency interference, even from the ground that can get into the feed horn. It can be picked up by the feed horn or side lobes. Steering the telescope is yet another big issue. Again, these are big machines. Wind and gravity loading, those are things that people have to worry about once they get big. Interferometry, we talked about that briefly. We can talk about these things in future meetings. And so that might be something that if you guys might know about antenna theory, that might be a great discussion point for a future meeting. But I'm not a ham operator, so I have very limited understanding. So I could really use the help. Okay, let's talk about my setup. So here's my 1 meter dish. I have it sitting on an iOptom Cube Pro mount that I bought. My gosh, it's probably 15 years ago. Here's a close-up on the screen. One of the things that is suggested is to put a wire mesh behind it. You can kind of see how I have it curled over and I have these little wires holding it in place. That backing screen, I believe, has helped reduce any interference from the mount itself. When I first was doing this, I had some really bad interference, but this seemed to help a lot. Here's the back view, just how it's attached. I got a counterweight on it. Here's the mount. And so this little black line, that's coming out of the antenna. And that's my sawbird. That's the H1 filter and low noise amplifier. Now, this is a little different than what Sandy has and what they recommend or talk about in those websites where they talk about building this. I don't have my RTL SDR sitting right under here, if you can see my mouse. In fact, I have it actually plugged into my laptop. You'll see that in a second. But I have a coax cable that runs from here to the SDR unit. And I did it for a couple different reasons. The SDR units, they get really hot. And I was thinking I could put it into like a cooler with some those little ice pack things to keep it from getting too hot. But it turns out it's not a big of a deal. I've also did some comparisons last night using the cable and just having the SDR attached directly to the Sawbird. And essentially, I got the same results, except I got some interesting, crazy radio interference when I had the dongle, the SDR right below here. So I guess I prefer having it this way, but it's your choice. Whatever you guys want to, do for your own application. Either one works. Here's my laptop. So I got you can see the SDR hanging right off the side there. And I'm running the SDR Sharp or Spice software. And I think last meeting, someone asked how do I sync this with the mount with where it's pointing at. What I do is I point it at the sun such that I have the shadow of that that little metallic, I don't know what you would call that, Sandy. It's I don't know what that is. It's the, go back. This thing right here, that little aluminum metal thing.
Yeah, I think there was it's either the reflector or the subreflector. It's
yeah.
You had it, yeah.
I'm sure what it does is it helps kind of gather the radio and kind of go into this little black where the receiver is.
That would be a waveguide going down.
That'd be what?
A waveguide going down.
Yeah, that could be. You're probably right. Okay, where am I? There. So I cast a shadow of that right on the back here, and then I just tell the mount to sync up with the sun, and then everything works great. It also works with the moon. So if you're at nighttime, if the moon's out, it'll work too. Okay, let me stop for a second here. Bring up. So I created this file, and I'll send it out to you, this PDF file at the end of the meeting here. But basically, I went and looked. These are all the links to get to the parts. You can get this grid off of eBay for $72.99. Here's the Sawbird, here's the RTL. There's actually two versions. I've been using a version 3. There's actually a version 4 out. I don't have that, so I'm assuming it'll work just the same. Same price, $37.95. Oops. This part connects from the telescope to the Sawbird. Here's a USB if you want to just attach the, if you attach the SDR right to the Sawbird, and you would use this to connect the SDR to your laptop. Male couplers, you need these if you want to connect the SDR right to the Sawbird. So that's how you connect those two together. You'll need a tripod or a mount of some kind. I've seen pictures of people throw the whole antenna into a box, a cardboard box pointing straight up. There's your mount. Obviously, if you have some kind of an equatorial mount or alt-az, you can steer and guide and move around, look at stuff, which is pretty convenient. But if you don't have that, you can still make it work very well. Now, recommended parts. We'll talk about this in a few minutes. When you calibrate this thing, there's two ways you can do it. You can either point the telescope or everything connected to it at a part of the sky where there is no Milky Way, and you let it run through a calibration sequence. I'll show you how to do that. Or, and this is what I decided to do, I bought these little terminators, 550, pretty cheap, and you screw it at, you take the Sawbird off of connection to the telescope, you screw that onto the end of the Sawbird, and then you do the calibration with that. And I think that delivers a little bit a better result. I tried the Sky thing, it doesn't work. This works actually much better. And for 550, that's, it's nothing. So I recommend that. And again, if you feel like you want to use that cable, here it is. It's $10. It's a 50 ohm. I think it's 16 feet long. And Sandy, we talked about that the other day. So like I said, I didn't detect any difference with or without using that coax cable. So in my particular case, it worked pretty well. But I think you had mentioned that you had read somewhere that it didn't work for somebody else.
Yes, there was a presentation a guy did for Sarah that he apparently on his rig was not getting good performance, and he moved the SDR up right next to the Sawbird. So he eliminated the communication between the amplifier and the dongle, as opposed to going across the line.
Yeah.
And, I assume that, I don't know why his particular rig that made the difference, but it did. And I guess the moral of the story is that just like what you're doing, the thing to do is to try different configurations and see what difference.
Yeah, I would just go with the SDR attached right to the Sawbird using these little couplers, because that's the cheaper way to go. And if you feel adventurous, you'll get the coax. See how that works.
I've got a question that Doug has again. He wants to know how much the mount cost, and I'm assuming he's talking about the mount that you use, that you've got yours on.
I don't know how much those cost now. I bought it back, like I said, probably around 2011 for like $400. I don't know if they even make them, but you might be able to find a used one. I had to get an upgrade to the GPS when we had that GPS rollover problem with a lot of the telescopes, but they had the parts. I did that like a year ago. They still had parts for it, so
Yeah.
So I don't know how much they cost now, but any alt-azimuth mount would work, or one of those strain wave ones if you have one of those.
And you really don't need a mount, I take it. You can just put
No,
it, like you said, in a box and point it straight up, and do a
Yeah.
drift scan. He also wanted to know which Windows version you're running on your laptop.
I'm running Windows 10 in my laptop, and I'll talk about that in a little bit with the processor in it. That laptop is at least 10 years old, and it works great. It works fine. It's not a huge load on the laptop, on the CPU.
I think Doug has got a question. I see him waving his hand. Do you want to take yourself off mute, Doug?
Oh, it's just being friendly.
Yeah, so my concern with the Windows on your laptop is, does the AirSpy software require a specific Windows version?
It works under Vista, Windows 10, Windows 11. So
Something new. It wouldn't work with something like NT or XP.
I don't know. I installed an x64-bit version today, but they have a 32-bit version as well. So I think it should be able to, I think it's backward compatible pretty far. As long as if you got a 32-bit machine, it should work fine on that.
Okay.
Moving along, the guy that talked about building one of these, the scope in a box, they talked about an alternative to the Sawbird, and that's this little unit here. It doesn't have a bias T. That, by the way, is, I don't know if that's a term that's a ham operator term or where that comes from, but the point is you actually have to have a separate power to come into it. The Sawbird gets its power from the RTL SDR dongle. And even with my cable, the power goes right through there too and powers it. So, and this actually costs quite a bit more, but I don't know if it's a better one or not, but that's just an alternative. And then this is an alternative SDR dongle that they recommend as well, they talk about. And lastly, software. So we want the SDR Sharp. They have a 64-bit version. They also have a 32. When you go to this website, you can see all the versions they've got right there. There is install that first, and I'll get into that a little bit, how we do that. The IF average plugin, that's the thing that's going to do the magic for us. That's the one that actually analyzes the signal, creates that really nice little chart that shows the signal in different wavelengths. And lastly, and this is something that you might find interesting, Sandy, there is an SDR Sharp average DLL upgrade. And if you install this, you get the version 2.8. I know you said you had 2.7 on yours. So this will bring up to 2.8, which is the most recent release for the IF average plugin. So like I said, I'll send this out so you guys can look at it. If you want to build one, you can just click on the links and see how much they cost, and you can order them from Amazon. Okay, let's go back to our slides, which are currently in progress. Let this go away. There we go. Okay, so how about some demo action here? I'm going to capture some stuff and we're going to analyze the data. All right, so let me stop that and bring up. So what I have outside, outside my bedroom, I'm in my office here. So on my patio, I've got the telescope sitting up there and I've got my laptop connected to it. In fact, let me, you can see this is, I have an i5 6300 CPU. And you can see it's right now actually using, analyzing the image coming in. And this is how much CPU time it's using. So it's not a whole lot. We got 16 gigs of RAM, 7.5 gigs are used. So plenty of space. All right, so what are we looking at here? This whole box here, except this. Don't look at this. Let's do this, make it go away. Okay, this right here is the SDR Sharp AirSpy app. Most of these controls, I have absolutely no idea what they do. And all these nifty little things over here. If you're a ham operator and you use this, you would know what these are. I just don't know. But I have it tuned in for the frequency for our 21 centimeter neutral hydrogen line. As I mentioned before, there is a plugin called IF Average. That's the screen right here. And if you look at the website, which I have also in that part, so I have at the top of the page, these are the settings they recommend. FFT, that stands for Fast Fourier Transform. Fourier transforms are used everywhere with radio astronomy. And the nice thing is we don't have to worry about it. We have software that does all that great stuff. But essentially what a Fourier transform will do, it'll take the signal, which is a mixture of different frequencies, and separate them out so we can get a spread like this with all the frequencies at the bottom like this. It'll spread them out, it analyzes and figures out the individual frequencies and the intensity. That's what that does. This average, since it's called IF average, what it's doing is it's averaging over a period of time the signal coming in, and it takes about 7 minutes to fully form the image. And I think it's using 902,000 samples to do that. I believe that's what that number stands for. Okay, so that's that. This screen here, this is the actual IF average screen that shows we're looking at something. And there's an interesting little peak right here. Now, I use cartes du ciel to control my telescope. I've been using it for thousands of years, so I still continue to use it. It looks great. Here's its screen. The circle here represents my field of view of my telescope, and I'm kind of have it centered on M80, just for the heck of it. So you can see here's Alpha Scorpii, Antares, and there's the 3 stars and the arms and all that stuff, the tails going on here. This is the area that we're looking at of the Milky Way. This gray stuff, of course, represents the Milky Way. I'd go over here, but there's like not much left. Maybe up in here, but this is getting, my neighbor's house is probably right in that area, so we can't look at that. I asked him to take his house down, but he wouldn't do it. I don't know why. Anyway, so that's what we're looking at right in this area here. And that corresponds to this little peak right there. In fact, I can play with the gain, you can move in different spots like that. Now these bumps right here, and over here, I think that's radio interference from my neighborhood. Because if I just track this, let the scope track it, the mount track it throughout the night, these disappear after a while. So that tells me that it's not part of the object that we're looking at, the Milky Way. And these, of course, these little tiny spikes that you see here, that's all some RFI coming from somewhere. And I don't know where that's coming from. Now, so this is cool. By the way, one of the things I wanted to talk about very briefly, and I think I talk about it later with the software, there is an analogy that we have to do in we do a calibration of the system that's very similar to what we would do for optical. It's very similar to flat fielding. And so they call it a background, and that's what these little buttons here are: acquire background, reset the background. I did that earlier. I used that little 50 ohm terminator on the end of my Sawbird. I let it run for 7 minutes while I had clicked the acquire background. And then I went down here and I saved it. So background save. And what that allows you to do, because it takes 7 minutes to do this, the next session, I just have to read that in. I don't have to go through that step. But if you don't do that, you get this really funky kind of a squiggly image. And I'll show a picture of that a little bit later on. Now, what if I wanted to get the data? I want to export the data of this image and put it into a spreadsheet. Well, that's quite easy to do. You go to the Save Single. I don't know if you can see the button there. And since I'm looking at M80, I'm going to call it M80. M80 signal. It's just a simple text file. And let's see. Get modified. Oops. I'm going to open this file up in Notepad++. So you can see what that looks like. You can see the 902,000, that's again matching this number here. I don't know what this first number is. It changes each time I run it, so I'm not sure what that is. But the interesting stuff is down below. So this represents the wavelength. This represents intensity. So it's wavelength intensity. And it creates 1,025 of them. So what I'm going to do is I'm going to, first I'm actually going to go to my spreadsheet. I like LibreOffice. I mean, I use Excel, but I kind of like LibreOffice a little bit better. So what I'm going to do here is I'm going to create another sheet. I'm going to call it 80. And I have these other ones. I'll show these in a few minutes. But basically, what I'm going to do is I'm going to copy and paste. Copy. Paste. Just change that to M80. Then I'm going to go back to my notepad. And I'm going to do is a Control A, copy, come back here. I'm going to copy that data into this particular tab setting. I'm going to do a paste special, unformatted. And if you remember looking at the file here, bring it up again. These are just simple spaces between. It's not like a comma separated list like you would get for you want to import it to Excel. So I just had to specify, I got spaces between them and just merge them, just count multiple of them as one. And this is what's going to look like. So I click OK, and boom, there's my data. And you can see I got these little spiky things. Again, that's RFI from the neighborhood. So this is the same image. Let me bring the other guy up again. That's essentially this image here. It's a little exaggerated, but that's the same image. This column here calculates the radial velocity using some of these constants up here, and that's what we see down here. So what we can conclude is that that region around M80 virtually has no radial velocity either approaching towards us or away, at least in this very simple calculation that we're doing. If we're going to do this right, we have to do, I forget what they call it, where you have these, sounds like the reference, center of rest reference or something like that. And that would probably shift this off a little tiny bit. I did this earlier today for NGC 2239, which is really close to Orion. And here's the signal that I got. So what's interesting is that it's definitely redshifted away. And you can see it's not just a spike, it's a whole kind of a nice sloping curve. And what we can conclude from that is that we're probably looking farther into the hydrogen cloud that's out in that direction. And those atoms are actually receding far faster away from us than the ones that are closer to us. And that's the kind of conclusion we can come to. Here's Cassiopeia A. I did that one last night. Couple bumps. Again, it's a little bit blue shifted, but there's definitely a significant bump here. These are two spiral arms, pretty much, as I understand it. And one is approaching us much faster at minus 50 kilometers per second. And I also did M57 last night. It's like, okay, it's approaching us at about, was that 20 kilometers per second? So you can kind of see the stuff you can do with that. Let's see, how are we doing time-wise, quarter till? If you want, I can move this to a different part of the Milky Way, and we can sit and wait for 7 minutes to see what happens. And in the meantime, we can entertain questions or talk about stuff. So why don't I go over
Hey, Gary, you hearing me?
Yep.
Yeah, I think the center of reference is referred to as rest frequency,
Okay.
if I'm not mistaken.
We're going to go to NGC 6535 to see what happens. You can see it's tracking the scope. Now we wait. I'm going to set my timer on my watch. This takes about 7 minutes. But what I want you to watch is that this peak is going to change. These little bumps might change. These little spiky things might change. But it takes about 7 minutes. If you get impatient, you can actually tweak with some of these numbers up in here, and that'll accelerate it, but the quality of the result won't be quite as good. How about this? When we're letting that thing run, how about if I continue this presentation slides for a few minutes, talking about the software itself? That sound good to you guys? Or do you want to watch that? Let's have a democratic vote. All right, we'll do the slide.
I would go to sleep.
Don't fall asleep.
While watching that, I would.
So now what I'm going to show here is a whole bunch of stuff. A lot of it's a repeat what's in the website that talks about building this, but there are a couple little things I changed on it that made it a little bit easier. So basically you download the SDR Sharp. You could do x64 if you've got a 64-bit laptop operating system, Windows operating system. If you don't, there's a 16 or 32-bit version out there as well. The IF average plugin works on either one. You can download it from here. I unzip it, in my case, to a directory called SDR Sharp-x64. Here's the instructions. There's very specific instructions you have to do to get it set up properly. That's all correct, what they have in there. As part of that, they talk about starting the SDR Sharp running. I decided to go all the way to the latest. They have two versions of the executable. There's a .NET 8 and a .NET 9. I decided to do the 9. If you do that, you most likely don't have .NET 9 on your machine, and it'll tell you have to install it. And if that's the case, you just install it, and then you go back and you rerun the .NET 9 executable again. After that, click the start button, and off you should go. You should be able to see the equivalent of that staticky screen that you had in that we saw earlier. Stop the program. We'll go to the next slide. Now we do the IF average plugin. You have to get it from GitHub. You got a button that you can click on to download a zip file. You unzip it someplace. Copy these files over. The instructions say to put these in a plugin subdirectory off of the SDR Sharp. I found that doesn't work. You got to actually put it in with the SDR Sharp. And then copy this file over. Oops. And then lastly, and this is the one that gets you the 2.8 version, you download the latest average and you put it both in the main directory and in this plugins directory. That's all you have to do, I believe. Attach your Sawbird filter, the dongle, start SDR Sharp, button, click the start button. They talk about adjusting the RF gain, bias T, you tune into the frequency that we want. Here's how to get the IF average plugin running. Here are the settings that I showed you earlier. Again, I don't expect you to remember all this. This is just give an idea what I have come up with here for you. Calibration. I mentioned earlier how important that is. You can use that 50 ohm terminator or use a sky that doesn't have the Milky Way. This is the equivalent of doing a flat frame. If you don't do it, this is the image you're going to get. I don't understand what that means. I don't know why it's even that way, but it's just funky like that. It's a property of the dish, I suspect. But after you do the calibration and you subtract out the background, again, without looking at anything, you get this perfectly flat line here, which is what you want. And then if you use a terminator, you reconnect it to the intended connector, and off you go. So move the terminator. I can do some observing, point the antenna somewhere at the Milky Way, wait 6-7 minutes. I talked about doing the save single button that you can do, and you can import that into Excel or LibreOffice Calc to create the graphs. All right, let's go back and see what's going on over here. Oh, so I don't know if you remember, but that last thing we looked at had a pretty much of a, it didn't have this little kind of sloping edge here. We still have our little RFI guys over here. According to my watch, I got about another minute for this to fully form. I believe this stuff here is probably something in the Milky Way as well. And once this is complete, we can import it in to the spreadsheet, see what it looks like, see what the radial velocities look like. So with about a minute left, any questions so far, thoughts?
Yes, can you hear me?
Yes.
So the parts listing that you compiled into a PDF, how is that going to be available?
So what I'm going to do is I'm going to zip up the presentation slides,
Okay.
the document you just referenced, the PDF, and also I'm going to include the spreadsheet file, this graphed observations.ods. I can put all that together in a zip file. We'll be able to get a list of all the attendees from Zoom, and they'll send it out to everybody.
Awesome.
So you guys can have at it. Okay,
Thank you.
it's done. My watch says it's done. So nice bump here. Interesting one over here. Let's see, what's it looking at again? Is NGC, oops, that's the wrong one. NGC, oops, 6535. Wink. Saved. Now, this is the one we just did earlier. Notice this 10-106-000. Now it's different. I don't know what that is. Maybe it's a timestamp. Not sure. Anyway, okay, so back to Calc. I'm going to create a new sheet. I'll put after it this time. I'll call it C65. 65. Can I type? No. 35. Paste. About that, come back to my Control A, copy here, a special. When is your last health check? Go away. Okay. There is our object. Again, let's confirm that's the great guy. Again, it's a little compressed, but you can see there are these bumps here. There's this little area in here. It's interesting. Radial velocity says that it's approaching us at about almost 20 kilometers per second. But there's parts that probably are maybe closer that are falling away a little bit slower, to the point where there's some actually receding away from us a little tiny bit. So that's pretty cool. At least I think so. At this point, that's all I have for the demo. Did you guys want to see anything else? Any questions on the screen? Actually, it's Q&A time. If I bring back my slide, next one is Q&A. Let's do Q&A.
Gary, this is Sandy.
Yeah.
You wanted to distribute a file that's a PDF that shows your parts list.
Mm-hmm.
I think you can do that from here.
Really?
If you want to. If you go to chat, and down at the bottom of chat, the third icon over is file. I think if you click that, you can actually grab something off your system and send it out to everybody via Zoom.
Okay. Let's see my incredible file system here. Okay, so it's actually a doc file. I haven't created a PDF yet. Oh wait, maybe I did.
The reason I'm saying this is that I was just looking into how one gets all the email addresses for participants, like we talked about the other day on Zoom, and it looks like there's a little bit of setup that might need to be done. So if you can distribute that right now, that would be preferable.
I'm going to right now. If I can get to work. I'm going to create the PDF for it right now. And then I'll send it out.
Yeah.
Okay, save as. Save as PDF. Do it. I have to oh, that way I do have it.
And by the way, my version of that parts list, because I put one of these together also, it was about $200 for all the parts here.
Yeah, so around 200. That's really a good deal if you ask me.
Of course, that doesn't include the mount or the laptop.
Right. Presumably most people have laptops of some kind or a computer. Not be seen because it's currently in use. What? I'm getting this message here. So let me close that. I tried again. I have to go all the way back. Sorry.
Maybe people can email you for the PDF.
Well, it'd just be a second here. I'm almost.
Okay.
Any questions so far? I mean, any questions about this?
I put this question in the chat, but I'll go ahead and ask it. So Gary, once you have your SDR and your Sawbird, that's the filter, right?
Yes.
And you've got your software installed on your laptop, you would use that whole setup for all of your different antennas, correct? You wouldn't need a separate SDR or a separate Sawbird for the different antennas, would you?
Yep.
I don't think you need to.
Okay.
The hobby is such that Just as in the optical, you could spend money out the wazoo on sophisticated electronics. But for starting out, you could use it with the Wi-Fi grid. I don't think it would work with an itty bitty telescope because those low noise blocks aren't really configured to handle the 1.4 gigahertz. They're looking for a much shorter wavelength. I think it's like 5. I mean, yeah, 5 gigahertz, something like that.
You
So
mean
I don't
for
think
the
it would work with
itsy bitsy?
those.
It wouldn't work for the itsy bitsy?
No, the itty bitty one, you need to actually get one of those satellite finders and attach it to your itty bitty that way.
Oh,
If you hang on, or I can find a picture of it.
but don't you still need an SDR and a filter?
Not for the itty bitty.
Oh,
Yeah. Okay, Swinburne. It's going to take me a moment or two to get the
okay.
find the picture. Okay.
Oh, that, okay. I
Yeah.
see.
So you plug the satellite low noise block into here. You have to build a little power supply and you plug it in here. This thing here is something I added to where I actually tapped into the signal coming into the meter and I had it running on going to an amplifier and I built all that. But in the simplest case, you can just use this. And when you're pointing at the sun, you'll see the gauge will go over.
Okay.
You can adjust the gain
So
with the
you're
knob.
not filtering for a specific wavelength or anything like that. You're just measuring signal strength.
Right. The wavelength is the same that the satellites use. And again, I think it's 5
Okay.
gigahertz. I don't know for sure.
Okay,
That's right.
gotcha.
And it just so happens because the sun is a black box radiator, it is actually emitting radio waves,
Sure.
those frequencies.
Yes, when it lines up with a satellite, that's when you get disturbances in your TV signal.
Yeah.
I gotcha. Okay.
Okay. That's all I have for tonight.
But
I
if you were to switch and build like the dipole antenna, you could still use your SDR and filter in line for that.
believe so. I think,
Okay.
again, when you do the dipole, you'll have to configure it. I think, was it a quarter wavelength long? I think
I
like
don't,
that.
I think so, yeah. There's measurements you take to get the right length, yeah.
Right. And essentially what you're doing, you're building a feed horn for that.
Okay, can I have some comments?
Sure.
Okay, just comments because you have questions, and I'm not familiar with Zoom. This is one of the first times I've used it. You mentioned a screen behind your itty bitty. That also helps that you have the holes get some of the ground noise. You're looking at the ground, you'll see that hot.
Yes.
It was very amusing to mention the FFT. When I was up at Alma at 18.5, they had the world's second highest building at the time, the fastest computer, but all it was doing was FFTs off all those antennas.
Yeah.
And if I have a chance, I'll show you my pictures. You question the bias T for your information that gets power into your coaxial cable, so it gets the DC power to where you're going or signal. You had that double hump. That was probably ground noise off your little feed. You know, you had the thing going up, and then you had so you're looking beyond it and get some ground noise. That's what I would say. Sandy, am I on for the 30th or the 23rd? You said 30th, for the 23rd is the 4th.
Whatever the third Wednesday is of July.
Okay, so a third Wednesday, I'll go for that. Okay.
Right.
Now, can I give my spiel now and then we'll forget it?
Now, first of all, Gary,
Yeah.
anything more?
I'm done. Any more questions?
Well, thank you very much, Gary. That was really very informative.
Yeah, great.
Thank you.
Stop sharing. You're welcome.
Go ahead, Vince.
Okay, I'm on tap for the next one, and I plan to cover the history of radio astronomy from even before Jansky, when they were trying to detect something out there, almost just before they came out with the irreversible, when they started really getting complicated. One of the amusing things, Gary, is that you show the neutral hydrogen line.
Mm-hmm.
I plan to discuss how they went about getting that and how that guy found a paper from Reber that interesting during the war. So we'll see how that goes over. The thing I'm interested in is on these topics. Is anyone interested in a little more detail on the components and how antennas work and how receivers work and all that kind of stuff? So we could make one of these presentations on that. And the other thing, since I'm a sort of an old guy, I missed the last meeting because I was in a hospital. If anyone else wants to take on some of these topics, go ahead. Some of you know more than I do. Most of you know more than I do anymore. So that's what I was going to show on the chart, Sandy.
That'd be,
Okay, go ahead.
sorry, I'm just commenting. That would be a good idea if you wanted to highlight on some of the components.
Okay, I mean, I can give a presentation on that. I mean, electromagnetic theory and antennas was my doctoral work, so I'm not unfamiliar with that. And, unfortunately, I'm too old to fix my current ham antennas. My wife won't let me go up on the roof anymore. When you hit 85, 86, it's sort of hard.
Yeah.
So anyway, all right, I will plan for that. I'll talk about that. What it's the third Wednesday, right? Yeah, Sandy.
That's correct.
Okay, well, I'm gonna have about the same number of charts, not as exotic as Gary's, but they'll be there.
Yeah, I can't help it. Sorry.
The other thing is I have a Mac here, so we got to figure out how to make my Mac presentation. There's got to be a way that they have to have it on Zoom, so I got to figure that out. So I'll do that on my own. And if we need to, I also have a Windows 11. I'm bilingual on Mac and Windows. Just I get confused.
Be happy to work with you on that. Bring up a test session and get that worked out with you before.
Okay, I'll send you
next
an
meeting.
email. We'll get that worked out so I can send you some stuff.
That sounds pretty good.
And the history is interesting because they were looking for the sun long before Jansky accidentally found it. And then and even in this era, several things were, what I say, they're saying, what the heck is that?
Okay.
And that's a major story of a lot of the earlier part, even now, of radio astronomy.
Okay, Vince, don't give your presentation away.
Oh, no. Oh, I will say I'm up to 7 sources of them, and they don't always agree. So, okay. I'm out of here.
Are there any other announcements?
You had mentioned early in the meeting about the space weather thing that I had talked about. Do you want, I think I can show a picture of my gadget if you want to see it.
Sure.
All right,
Sure.
let's see if I can do this. Share screen. Let me bring up space weather. Okay, share screen.
It's being stingy.
Okay.
Okay.
Okay, can you all see that?
Yep.
Yes.
That's the gadget. It's a
It's bring,
2-liter soda bottle.
Could you zoom in on that a little bit or open it up?
we're
Uh,
seeing all kinds of
Thumbnail.
files there.
Yeah,
thumbnail.
files.
Oh, really?
Yes.
Okay,
I
Oh,
think
you're
you should,
sharing the wrong screen.
I've got mine shows the big, the one frame. I don't understand.
Ours is seeing, about
I think we're
9,
seeing
10,
the
10,
file
9 or
explorer.
10.
All right, hang on.
images.
Let me try this a different way. All right, let me stop that. Okay, now let me try sharing. How's that?
That's
Yes.
good. That's good.
Hey, there it is.
Okay. All right, so it's real simple. It's 2-liter soda bottle. I've got a magnet hanging there.
Mhm.
Okay. And the little flat mirror. There's dirt in the bottom, that's ballast to keep the bottle from falling over, basically. And you bounce a laser beam off that mirror, and you can measure how the magnet swings as the magnetic field changes over time. Okay, and that's it. That's all you do, and you record your measurements over a period of 100 days, is what they say in the requirements for the program. And when there's some unusual activity on the sun, you might see a swing of the magnet.
So your laser is pointing at the mirror and that's reflecting onto like a chart or a wall or something?
I'm bouncing it from, I've got a fixed location where my laser is. I've got a fixed location where the bottle is, and the laser beam hits that mirror and goes on the wall, basically. And I'm measuring its position on the wall so I can see how it changes from day to day as it swings back and forth. And according to the program, according to the write-up in the Astronomical League website, whenever there's unusual sunspot activity, there's something called the K index, which is a measurement of you guys with amateur radio guys are probably very familiar with that. When that K index gets high, it has an effect on the Earth's magnetic field, and that'll change where the magnet is pointing, and you'll detect that. It'll swing back and forth. Haven't seen anything yet because I've only been running it for 5 days. But according to what the Astronomical League website, it says we should, because we're still pretty close to solar maximum, we should pick up some activity in the next few months. So
Yeah,
okay.
it's very active right now.
Yeah, I'm going to do a workshop on this. We're going to supply the magnets and the little mirrors and the other material. All you'll have to do is bring your own bottle. And,
UIOB, huh?
yeah, and I'm probably going to schedule a workshop, in August, I think, maybe September. But we're going to have some fun with it. So, but this one, it actually, I found this particular program by accident, because if you look at the Astronomical League program for the radio astronomy, it's down there in the section where it talks about monitoring space weather with your radio telescope. It says, well, if you're interested in space weather, we have an observing program for that. So I clicked on that link and it shot me to the space weather observing program. And this is what you build. So it's like, okay.
Pretty good.
So there's supposed to be a pole shift coming on the Earth. You'd be able to detect that too.
Yeah, if that happened, you definitely detect that the magnet would flip 180 degrees.
Yeah, we'd all be upside down then.
Okay, thanks for that, Doug.
Okay,
Stephen, did you have a question?
Gary,
You,
first, I want to thank you. That was a fantastic presentation.
Oh, you're welcome.
Yeah.
Thank you.
yeah, thanks, Gary. Yeah,
Hope you guys-
go ahead, Stephen.
Yeah, a question for Gary that I missed on the presentation. With the dish that you have on your scope, was that a homemade dish or is that something that you bought and modified?
It's something you buy.
Okay,
You can get on Amazon. That document that I'm going to send out, which I was unable to send out for some reason through Zoom, it's got a eBay link in there that you can get it for $72.99.
okay. And my second question is with the display on the computer, I'm totally blind to this. What is that display displaying? You got a bump there, but what are the axes? I couldn't read the numbers.
Let me share it again.
It's
These are,
wavelength versus amplitude, right?
Okay.
yeah, these are decibels. That's
Okay.
And then down here, of course, these are the actual wavelengths. Or, I'm sorry,
Okay.
frequency.
Okay. Okay. Cool.
And again, this is part of the plug-in. This part here is the plug-in. If I click on the radio, this is all the SDR sharp. This is a waterfall thing, I guess. I'm not sure what we're seeing here, but
Looks to me like raw data.
Okay. Cool.
Yeah.
Thanks.
you bet.
Okay, any other comments or announcements?
Thank you, Sandy, for setting this up.
Okay, thanks. Happy to do it. I think we're going to learn a lot all getting together like this.
Yeah.
I've learned a lot already.
You know,
Hey,
I think we should.
Andy,
I was going to say we should do the Astronomical League suggestions. Maybe we should use those as some of our goals to get a bunch of us in that category. You know, the bronze and silver.
that reminds me.
Actually, when we gave the presentation to the board, that is what we were suggesting, is that we use the Astronomical League's award system, something as a guideline, a blueprint for going ahead with our projects.
So
That's what
Sandy, it sounds like you probably have already qualified for one of the awards too.
Well, close to it. Yes, that bronze one would be pretty easy for a couple of us to get, I think.
Yeah. By the way, this book, Radio and Radar Astronomy Projects for Beginners, I purchased it for our library. I'm reviewing it now, but this is going to end up in the library in the next couple months.
Okay.
And we got to figure out at some point how to build a club one. It shouldn't be too hard.
Oh, that's different.
Okay, well, if there's
Okay.
nothing more, I'm going to stop the recording. And this recording will actually be then loaded out later to YouTube, and you'll need the exact URL to view it. So I think Gary and I will work on figuring out how to really get this sent out to everybody in this meeting so that you're able to look at the meeting later on. So I'm going to stop the recording now.